I'm Mercarenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Except this time, we're not going to be solving Project Euler. Last time, we found all of the amicable numbers less than 10,000 and summed them. An amicable number is part of an amicable pair, which is two unequal numbers whose proper divisors sum to each other. We solved this problem in APL, and this was our program. Today, we're going to get some more practice with APL and array-based programming in general. If you didn't watch the previous video, I recommend you go watch that one first, as I'll be assuming basic knowledge of APL and function trains this week. Now, this week, we won't be solving a Project Euler problem. Instead, we're going to solve a problem from the Code Golf Stack Exchange website, which I'll introduce later. First, let's talk a bit more about APL. For the problem we'll be tackling in a bit, there's some more tricks we're going to need to know. To start with, the function we wrote last time to sum the proper divisors of a number was fairly simple. It was so simple, in fact, that we were able to write it as a train of smaller functions in tacit style. While it's technically possible to write any APL function as a train with enough patience, it can detract from readability if not used sparingly. Fortunately, APL gives us a couple of ways to write more typical functions that take explicit arguments like you might expect. There are two forms of function declarations in Dialog APL: traditional functions and direct functions. Traditional function declarations, or tradfuns, were the original way to write explicit functions in APL. A traditional function is delimited by upside-down triangles called nabla or sometimes del. On the same line as the opening nabla, we put the function's header. This is an example function header for a dyad. R is the name of the result variable, x and y are the names of the two argument variables, and function name, naturally, is the name of the function we're defining. Inside the function body, we can do pretty much whatever we like, including assign to other variables. At the end of the function, the value of the variable we declared as our result, r in this example, is used as the return value of our function. The function body is then terminated by a line which contains only a nabla. The parallel sum of two numbers, commonly written as a double vertical bar, is equal to the numbers reciprocated, then summed, and then reciprocated again. This is useful in electrical engineering as a companion to ordinary addition. For instance, the total resistance of a collection of resistors connected in series is the sum of the individual resistances, but the total resistance of a collection of resistors connected in parallel is the parallel sum of the individual resistances. We can write the parallel sum as a dyadic tradfun like so. The first line is the tradfun header. The function we're defining is called parallel, our two arguments are called x and y, and the variable into which we'll store our result is called r. The body of our function consists of only one line, which binds our result to the r variable. We reciprocate x and y, then we add the reciprocals, and finally we reciprocate the result of that. Remember that the division sign, when used monadically in APL, reciprocates its input. Note also that we're leveraging APL's right-to-left order of operations here. The leftmost division sign will reciprocate the entire sum, not just the first term, since functions always take as much as they can for their right argument. As an added bonus, our parallel function already broadcasts over arrays. If we pass an array as either argument, or same-length arrays as both arguments, then the monadic reciprocal and dyadic sum broadcast, so our function does as well. If we wanted to define a monad using tradfun style, we would simply omit the left-hand argument, and the resulting function would be usable as a monad. Note that tradfuns don't implicitly declare local variables. If we assign to any variables other than our two arguments or our result variable, a tradfun will treat the given variable name as a global variable. To declare additional variables local to our tradfun, we need to place their names on the header line preceded by a semicolon. Tradfuns are nice for long functions, especially those that need to branch or communicate with external media, files, or devices. But for a nice short function like our parallel add, some more compact syntax may be warranted. This is where direct functions or defuns come in. A defun is declared by enclosing its body in curly braces. Inside the body, we can do pretty much whatever we can do inside of a tradfun, and the last expression is implicitly returned, similar to functions in Ruby. Inside our defun, the left-hand variable is called alpha and the right-hand variable is called omega. Be careful, these aren't the Greek small letter alpha and omega characters. They're APL functional symbol alpha and omega characters. We can rewrite our parallel sum as a defun like this. To write a monad, we simply don't use the alpha character. Defuns are nice for shorter functions, especially those fitting on a single line, and can be more readable than their tacit alternatives. Speaking of tacit alternatives, in case you're curious, here's our parallel sum function written tacitly. The circle here is called circle diaresis, and represents the over operator. Over takes the function to its left, and the one to its right, and produces a new function, which applies h to its argument or arguments, and then passes the result to g. When used monadically, it's simple function composition, equivalent to a top or a simple two-train. But when used dyadically, it applies h to both arguments before passing them on to the dyadic g. Then our entire function is a two-train where the first function is monadic reciprocal, and the second is the result of our over operator. And a two-train, when used dyadically, forms in a top, which applies the right-hand function to both arguments dyadically, and then the left hand monadically to the result. All in all, this is equivalent to our other two functions and performs a parallel sum in a mere 4 characters. Now that we know how to write functions, we're going to need to talk about some more built-ins. The program we'll write in a minute is going to be a bit more involved than Project Euler number 21, so we'll need access to a few more APL built-ins than we used last time. Last week, we saw drop, written as a down arrow. It takes a number on its left side and an array on its right, and it removes elements from the beginning of the array. If the input number is negative, it removes from the end of the array instead. The companion function take is written as an up arrow. It takes the same arguments as drop and returns, effectively, the part that drop removed. So with a positive input, this would return the first 2 elements, 1, 2. With a negative input, this would return the last 2 elements, 4, 5. A useful corner case of take is what happens when we pass a number bigger than the length of the array. In this case, the array will be padded with its type's fill element, which is 0 for numerical arrays and a space for character arrays. So taking 5 elements from this array, we'll take the first 3 and then need to add 2 more at the end. Thus we'll get 2 zeros at the end to fill in the missing spots. On the other hand, here we try to take 5 elements from the end of the array. So we take the 3 we actually have and then need 2 more. The 2 zeros will appear at the beginning of the result this time. Last week we saw that iota, when used monadically, represented the index generator function, which produced an array of numbers up to some specified limit. When used dyadically, iota is the index of function. It takes an array on its left-hand side and a needle on the right, and it searches for the needle in the left-hand haystack. In this example, we search for the number 30 in the left-hand array. The number is at position 3, so the result is 3. Remember that APL is 1 index by default, so the first element in an array has index 1, not 0. If the needle appears multiple times, then the index of the first occurrence is returned. And if the needle doesn't appear at all, then the index of 1 past the end of the array is returned. In this example, the number 30 is not present in the array. So rather than returning a valid index into the array, we return 5, which is 1 past the largest valid index of the array, 4. Finally, the right-hand argument can be an array, and APL will search for each element of that array independently. Here we've passed 3 separate needles to search the same array for. The number 50 is found at position 5, the number 30 is found at position 3, and the number 99 is not present in our list at all. So the resulting array consists of the number 5, indicating the index of the first needle, then 3, indicating the index of the second needle, followed by 6, indicating that the third needle was not found at all. The dyadic bottom symbol, written as an uptack, is the decode base function. The right-hand argument is an array of numbers, which will be interpreted as digits in some radix. The left-hand argument indicates the radix, and the returned value is the number represented by the digits in the given radix. For instance, a 2 on the left indicates that the array should be parsed as a base 2 or binary number. The digits on the right are 1, 0, 1, 1, 0. So to convert that number from binary to an ordinary decimal value, we write the powers of 2 underneath, multiply it out, and sum the result. In this case, we get 2 plus 4 plus 16, or 22. As an interesting side effect, this same function can be used to evaluate polynomials. Suppose we have this polynomial, x to the 4th plus 3x cubed minus x squared plus 6. We can represent this polynomial as an array of its coefficients by 1, 3, minus 1, 0, 6. And if we want to evaluate this polynomial at, say, x equals 3, we can simply use the decode base function with a radix argument of 3. To do the decode base calculation, we take 6 times 3 to the power 0, we add 0 times 3 to the power 1, then minus 1 times 3 squared, 3 times 3 cubed, and 1 times 3 to the 4th, for a total of 159. Obviously, 6 is not a valid digit for a number written in base 3, but the decode base function specifically doesn't validate the range of its inputs, so we can do this exact trick. This function can also take an array as its left-hand argument, but this doesn't quite do what you might expect at a first glance. Take a look at this expression for a moment. The result of this APL expression is 111. See if you can figure out why. Up until this point, we've been treating each digit of our input number the same. That is, when decoding a number in binary, every digit is treated as a base 2 literal. But there's no theoretical reason that every digit has to have the same radix. Our left-hand argument here informs APL to decode the number in the mixed radix 2, 8, 10. That is, the first digit, counting from the right, will be treated in base 10, the second will be treated in base 8 or octal, and the third will be treated in base 2 or binary. So when we calculate the resulting number, we take the 1, and then we add 3 times the first radix of 10. Finally, we add 1 times the radix so far, which is 8 times 10, or 80, for a total of 111. This may seem ludicrous at first glance, but it can be used to simplify unit systems. Suppose I give you an elapsed time interval, say 2 days, 4 hours, 30 minutes, and 10 seconds from right now. We can use decode base to convert this to a total number of seconds. That's because the number I just gave you, 2, 4, 3, 10, is just a mixed radix representation of seconds. Specifically, the radix is 7, 24, 60, 60. This will tell us that my number is 189,010 seconds. Where did I get this radix? There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 7 days in a week. Check the math yourself. You'll see that the calculation you perform on paper to find the number of seconds is exactly a mixed radix numerical conversion, just like we did for our hypothetical 2, 8, 10 example just a moment ago. Now let's talk a bit more about arrays. Remember that APL is an array-based language, and the language doesn't shy away from multidimensional arrays, or higher-ranked tensors, as we call them in the world of pretentiously fancy words. One of the most fundamental things we can do with a tensor is get its shape. The shape of a tensor is the array of its dimensions in order. In APL, we get the shape of a tensor with monadic row. The argument to monadic row can be an array of any rank, but the result will always be a one-dimensional array. The shape of a one-dimensional vector is an array of one element, its length. The shape of a matrix is an array of two elements, the height and width, in that order. The shape of a rank 3 tensor is an array of three elements, indicating its dimensions in order, and so on. The rank of a scalar is the empty array, as a scalar is trivially a rank 0 tensor. This raises the question. In APL, we can write scalars as simple literals into the code, and we can write rank 1 vectors as sequences of numerical literals separated by spaces. But how do we actually write higher ranked tensors, such as matrices? That's where the reshape dyad comes in. Reshape shares its glyph with the shape monad, as both are represented by the row character. Reshape takes an array of any shape on its right and a one-dimensional vector on its left. First, it flattens or ravels the right-hand argument into a one-dimensional array. Then it reshapes it so that the eventual shape is the one specified on the left. So if we passed reshape a 3x3 matrix and gave it a shape of 9, it would flatten the matrix into a vector of 9 elements in row major order. We could also do the reverse. If we give reshape a 9-element vector and a shape argument of 3, 3, it would produce that 3x3 matrix. This is the most common use of reshape, to construct a higher tensor from a literal one-dimensional vector. If the right-hand argument has more elements than we need, the extras are harmlessly dropped. If the right-hand argument has too few elements, the raveled list is repeated cyclically until we have enough. This can also be used to repeat some lists to a certain length. Speaking of raveling or flattening, the monadic comma will perform this operation. It takes an array and produces a rank 1 vector of all of the elements in ravel order. That is, it flattens an arbitrary ranked tensor into a rank 1 tensor, keeping the elements in the same order. Dyadic comma is the catenate function, which joins two arrays together on their final axis. That is, it concatenates two rank 1 vectors. If given a pair of rank 2 matrices, they'll be concatenated horizontally. Now is a good time to interject that many functions in APL can take an optional axis specification. After the function's name, but before its right-hand argument, we can write a pair of square brackets with one or more numbers inside. This tells APL which axis or axes to apply the function along. By default, catenate applies to the final axis, which means matrices will be joined horizontally along axis 2. But we can specify axis 1 in brackets to get a vertical concatenation. If all you want to do is concatenate on the first axis, you can also use the dyadic comma bar, which works just like the dyadic comma but defaults to the first axis rather than the last. You might recall dyadic // or replicate from the last video. Replicate repeats each element of the right-hand array a number of times specified by the left-hand array. So if we feed it snowman and the repeat counts given here, we'll repeat the first character once, then we skip over the n, repeat the second character twice, then skip all the way to the terminating n and repeat it once, getting the word soon. Dyadic / is called expand, and it does sort of the opposite operation. For positive integer arguments, it just repeats the elements in the same way as replicate. However, negative elements in the left-hand array cause padding, in the form of fill elements to be added to the result array. Here, we repeat the s twice, then we repeat the n once. Next, we have a -3, so we insert 3 copies of the fill element, which for a character array is a space. Then we write O and repeat W twice. In general, the number of positive values in the left-hand argument must match the number of elements in the right-hand argument. Like the // / can also be used as an operator. The // operator is reduce, which folds an operation over an array. The / operator is scan, which does the exact same thing but saves intermediate results. So plus / sums an array. 1 plus 2 plus 3 plus 4 plus 5 is 15. Plus / does the same thing, but it remembers each step. We get a 1 from the first element, then 1 plus 2 equals 3 for the second, then 1 plus 2 plus 3 equals 6, 1 plus 2 plus 3 plus 4 equals 10, and finally, the sum of all 5 elements, or 15. The monadic circle with / is the transpose operation, which does basically what it sounds like. Given a matrix, it returns the transpose of the matrix. In general, for an arbitrary ranked tensor, if the input tensor has shape ABCD, the resulting tensor will have shape DCBA. That is, transpose always reverses the shape vector for an array while keeping the contents the same. Dyadic circle style is the rotate function, which shifts its right-hand array by a certain amount specified by its left-hand argument. By default, rotate operates on the final axis, but we can provide an axis specification to override this. Dyadic circled minus is called rotate first and works like rotate, but defaults to the first axis rather than the last. One of the major differences between J and APL is in their handling of nested arrays. In J, every array has a type indicating what it's allowed to contain. Arrays cannot directly contain other arrays, as the J designers decided it was too confusing to allow both higher dimensional and nested arrays. APL has no such restriction. Arrays can contain elements of any type, including other arrays, and don't have to be homogeneous. But what if we really want to nest arrays in J? We can still do it, but J forces us to mark our nesting explicitly. In J, the monadic less than verb takes a value, whether a scalar or an array, and wraps it in a box. A box is a valid data type that contains any one datum. And boxes, even those that contain different types, can be elements of arrays. So you can't have an array of arrays, but you can have an array of boxes which happen to contain arrays. It's just a more explicit way of doing the same thing. Similarly, you can't have an array that has numbers and strings in it, but you can have an array of boxes where some of those boxes happen to contain numbers and others happen to contain strings. In APL, the monadic subset symbol represents the enclose function, which takes an arbitrary value and adds an extra layer of array nesting to it. Specifically, it always returns a single element array whose sole element is the input. Even though APL doesn't actually have a box type, I'll often draw nested arrays inside of boxes just for demonstrative purposes. So the less than sign in J actually puts a value in a box. The subset operator in X, called enclose, just puts an array inside of a nested array, but I'll still draw it with a box to make it clear. The left inverse of enclose is disclose, written as superset. Disclose returns the first element of its argument in Ravel order. We briefly mentioned indexing into an array in APL in the last video. You can place brackets after the name of an array and then put an index to return a specific place in the array, just like in conventional programming languages. We can also index with the dyadic quad, called the index function. Index takes a position on the left and an array on the right and returns the element at that position. So if we ask for the second character of the character array zebra, we get the letter E. Index can also be used on higher ranked tensors to access smaller portions of them. If we try to index into a matrix with a scalar, we'll get a row. But if we pass index 2 arguments on the left, we'll select the specific element at that position. Each element of the left-hand array can itself be an array, which allows us to specify multiple elements to get at that index. This is an insane amount of power, but by far the most common way we'll use this is with a single array that's been enclosed once. In this form, the indices are not referencing different dimensions, but are instead referencing different positions along the first axis. So here, we would return the 3 characters EBR at the positions 2, 3, and 4. That's all of the new functions we'll need. Now it's time to talk about operators. Recall that an operator in APL takes 1 or 2 function names as arguments and produces a new derived function, acting as a sort of higher order function. Last time, we talked about the each and reduce operators. Today, there's a few new ones that we'll need. First and simplest, we have the tilde diaresis. Tilde diaresis always takes a dyad as its sole argument, and the derived function it produces is ambivalent, which means it can be used either monadically or dyadically. Used dyadically, it flips the arguments and passes them to the original dyad in reverse order. Used monadically, it duplicates the argument and passes it on both sides of the original dyad. Next is the power operator, written as a star diaresis. The power operator takes a function on its left and a number on its right, and repeatedly applies that function the given number of times. For instance, monadic white circle is the pi times function, which multiplies its input by the mathematical constant pi. Then white circle power 2 is a function which multiplies its input by pi twice in a row. White circle power 3 multiplies its input times pi 3 times, and so on. When the derived function from the power operator is used dyadically, the left-hand argument becomes fixed. So this expression takes the number 5 and then multiplies 2 into it 3 times in a row, getting a net result of 40. As a very special case, assuming the left-hand function is a built-in APL function, or a tacit composition of built-in functions, we can actually pass a negative argument to the power operator. This applies the inverse operation a specified number of times. So this expression will take the number 5 and divide rather than multiplying by 2, 3 times in a row, eventually getting 5/8, or 0.625. There's just one more operator we need to talk about today. The dot in APL performs advanced products of arrays. In its simpler form, dot is an inner product. It'll be easier to explain this one with an example. The function on the right of the dot indicates how to combine corresponding elements of the left and right arrays, and the function on the left indicates how to combine all of those intermediate results. So this application of the inner product reads, multiply the vectors pairwise, then sum the result. That's right, it's the dot product of two vectors from pre-calculus. We'll get 1 times 4 plus 2 times 5 plus 3 times 6, or 32 in all. The inner product always applies to the final axis of the left-hand argument and to the first axis of the right-hand argument, and those two axes are required to have the same length. If our left-hand array has shape 3, 5, 6, and our right-hand array has shape 6, 4, 4, then the result will have shape 3, 5, 4, 4, merging the two middle sixes. If you have any background in linear algebra, you've probably immediately recognized a use for this. Not only can we use the inner product operator to compute dot products of vectors, but we can also multiply matrices with it. Matrix multiplication can be summarized as take the final axis of the left matrix and the first axis of the second, multiply corresponding elements, and add the result. In fact, the same sequence of 3 characters can also multiply a matrix by a vector or a vector by a matrix. If the ranks of the two tensors line up, APL will just do what you expect here. Finally, if the left-hand argument to the dot operator is the special symbol called the ring operator, then we perform an outer product rather than an inner product. Now, rather than combining the final axis of one argument with the first axis of the other like we did before, we simply apply the operation on the right to every possible pair from the two arrays. This will produce an array of a much higher rank than the original. You can think of this as being sort of like the Cartesian product in set theory, just with a different shape. If we take two rank 1 vectors and perform the outer product with times as the operand, we'll produce a multiplication table consisting of every product of an element from the left with an element from the right. In general, the result will have rank equal to the concatenation of the input ranks. So if x has rank 3, 5, 6 and y has rank 6, 4, 4 as before, the result will have rank 3, 5, 6, 6, 4, 4. Now we have everything we need. Here's the problem we're going to solve today. This programming challenge is based on Super Mario Galaxy. In Super Mario Galaxy, there are 2 levels where Mario runs around a funny-shaped planetoid collecting musical notes. But whenever he steps on a tile, that tile starts to disappear. Like any healthy planet, this one features a black hole in its center. So if Mario falls off the edge or steps on a location where the tile has already disappeared, he's done for. Now, the shape in question is a rhombocube octahedron with the triangular faces removed. For those of you who are not sentient dictionaries that have learned to browse YouTube, you can think of it as a cube with the faces separated and then joined to adjacent faces by a bridge. Each face of the cube consists of a 2x2 square of platforms, and the bridges joining them together are 2x3 in size. We assume Mario starts at the lower right corner of one of the faces, then the input to our program is a sequence of 0 or more instructions, telling Mario to go up, left, down, or right. The goal of the challenge is to print out a simple boolean indicating whether or not Mario survives. Mario survives if he makes it to the end without falling into the black hole. There are 2 ways he can fall into the black hole. First, he could simply walk off the edge of the rhombocube octahedron into one of the triangular faces that we removed. Alternatively, he could walk back onto another position that he's already visited, since the platforms disappear when he first visits them. So, for instance, suppose our only input instruction is up. Mario walks up once, and the platform at its original position disappears. The program ends, and he's still alive, so we would print true. On the other hand, if our input was up-down, then Mario would walk up and then back down, falling into the hole that he just made and resulting in his untimely demise. Likewise, if our input was down right, then Mario would walk off the edge of the rhombocube octahedron, and we would still lose the game, even though we never revisited the same position twice. And yes, I'm actively looking for excuses to say the word rhombocube octahedron more often. Before we discuss our solution to this problem, we need to take a brief detour into abstract algebra, specifically group theory. In the 19th century, mathematicians observed some similarities in a lot of the binary operations we use in everyday mathematics, and they decided to put a name to those similarities. A group is a set of values together with a binary operation. We often write this operation as an infix dot, though it doesn't have to be traditional numerical multiplication. It does, however, have to satisfy a few key properties. Firstly, the operation has to be associative, which means that if we have 3 or more terms being combined by our group operation, we can put the parentheses in any order we like and get the same result. Second, the operation has to have an identity. That is, there must be a single designated element which, when adjoined via the group operation with any other element, produces that other element. The identity must be both a left and a right identity. We usually write the identity as a lowercase e or sometimes an epsilon. Finally, every element must have an inverse. That is, given any group element A, there must be a group element A inverse, which cancels off with A. That is, A adjoined A inverse and A inverse adjoined A are the identity. We'll often write the inverse with a superscript -1, similar to how we write reciprocals, but again, this doesn't necessarily have to be a multiplication operation. There are tons of examples of groups that we use in everyday arithmetic without even noticing it. Real numbers form a group under addition, and the non-zero reals form a group under multiplication. We can't include 0 in the multiplication group since it has no multiplicative inverse, and the group laws require every element to have an inverse. Note that I never said anything about commutativity. That is, although we can reparenthesize group operations, we can't necessarily swap the order of operands to our group operation. So if we restrict ourselves to looking at square matrices of a particular size, matrix addition and multiplication each form groups, even though matrix multiplication is not, in general, commutative. There's one more major example of groups that will come in handy in a few minutes, and those are the permutation groups. Given a set of elements M, consider the set of functions from M onto itself. This isn't a group yet, but if we restrict ourselves to looking at bijective functions, that is, those which have inverses, then we get a group under function composition. That is, the act of composing two bijective functions together to get a new function which applies the two in order is a group operation. Function composition is associative, it has an identity, namely the function which maps every element to itself, and every element has an inverse since we restricted ourselves to only looking at bijective maps. We usually write the permutation group for a set M as sim of M, short for symmetric. If M is the numbers from 1 up to some limit n, we simply write it as S subscript n for short. Now, let's talk about Mario's satellite problem. I described this rhombocube octahedron as a set of 6 2x2 squares joined by 2x3 bridges, but that's not how we're going to write our program. We're going to start with this figure. This figure is the perfect shape for our problem description. We can realize our rhombocube octahedron as a cube where this figure appears on each face. Put another way, this figure appears tessellated on the faces of our cube. Our tessellation figure appears exactly 6 times, laid out neatly on the rhombocube octahedron. Although this isn't technically exactly the same shape, from the perspective of which tiles are connected to which, this is equivalent to the 3D figure we described earlier. And the tiles are all we really care about, so that's good enough for now. The fact that these two spaces are equivalent up to connectivity is called a homeomorphism. We say these two spaces are homeomorphic, which means they have the same topological properties. The benefit of a cube shape is that we can simply represent Mario's position as an array. Specifically, Mario's position can be represented at any given moment as a 3-tuple f, y, x, where f is the face of the cube we're on, and y, x is the two-dimensional position on that face. This simplifies our problem, but we still have another issue. This cuboid representation doesn't yet handle Mario's direction. Direction is important as Mario can end up at the same position facing different ways. Let's consider 2 examples. First, Mario starts at the lower right corner of a face of our choice, then he moves up 11 times. This puts Mario on the opposite face of our shape on the square part. Now suppose instead that Mario's brother Luigi begins at the starting position, but moves right 9 times instead. Mario and Luigi end up at the same position on the bottom of the cube, but they're not facing the same way. If both of them try to follow an up instruction and move up from their current perspective, they'll end up moving in opposite directions. So it's actually not quite sufficient to represent Mario's position as a 3-tuple of face, y, and x. There are 6 faces on the cube and 4 possible directions for Mario to be facing. So in total, there are 6 times 4 or 24 possible states for Mario to be in, where his state includes his face and his direction. We'll represent Mario's position as a 3-tuple s, y, x, where S is Mario's state and YX is the 2D position as before. In effect, we represent Mario's position as a 3D position, where the third dimension is just our made-up state space. Now, let's take a look at how Mario moves around this cuboid shape. As I said, we're considering this as a cube with our tessellation figure planted on each face, so I'm going to show a cube right now. If Mario's in the middle of a cube face, then movement is easy. We just change the x and y coordinates by the correct amount and call it a day. The state coordinate stays the same because we're still facing the same way and we're still on the same face of the cube. Additionally, since we're treating Mario's direction as part of his position, we don't have to worry about rotating the directional instruction. Assuming Mario is not at the edge of the cube face, up always means decrease the y coordinate by 1, right always means increase the x coordinate by 1, down always means increase the y coordinate by 1, and left always means decrease the x coordinate by 1. Remember, these are deltas in our 3D coordinate system, s, y, x. Now comes the natural question. What happens when Mario does inevitably get to the edge of a face? Let's imagine Mario is at the top of a face and moves up. We need to wrap around and end up on the bottom part of another face. If Mario started at position s, y, x, then he'll end up at position t, y plus 4, x. The yx part is straightforward, we just wrap around. And our tessellation figure is 4 blocks high at its highest. So we increase the y coordinate by 4. The trick is finding out what our new state t is. To figure out what face and direction Mario ends up on, we need to figure out how to rotate the cube in a given direction. A cube consists of 8 vertices, which we'll label from 1 to 8 like so. Furthermore, any rotation of a cube will preserve opposite vertices. In this diagram, vertices 1 and 8 start out opposite one another, and any rotation of the cube will still see those vertices opposite one another. So really, we have 4 vertices we care about, and the other 4 can be labeled as simple opposites of the first 4. Now, rotating this cube involves permuting these 4 points in some way or another. That is, we can view the valid rotations of the cube as elements of the permutation group of these 4 points that we care about, S4. In fact, the group of rotations of the cube is exactly the permutation group S4. Let's take a moment and see why that is. We've already established that the group of rotations of the cube is a subgroup of S4, since every rotation of the cube can be viewed as a permutation. On top of that, we know how many elements this rotational group has. We already did this calculation once. There are 6 faces on the cube, and 4 possible directions each face can be turned in, so the number of possible rotations of the cube is exactly the number of face times direction states Mario can be in. And that's 6 times 4, or 24. We also know how many elements are in the permutation group S4. The group S4 consists of all of the bijective or invertible mappings from a set of 4 points onto itself, and it's a basic argument of combinatorics that the number of bijections from a set onto itself is n factorial, where n is the size of the set. Our set has 4 points, so the size of the permutation group S4 is 4 factorial, which is also 24. Our subgroup and supergroup both have size 24, which means they must be exactly the same. With that out of the way, back to our original question. Mario started at position SYX on the cube. He just walked off the top of the cube, and we've determined his new position is t, y plus 4, x. For some t. We can now identify this value of t. When Mario walks off the top of the cube, this is equivalent to Mario remaining in place and the cube rotating downward to compensate. So Mario's upward moving state change corresponds to an element of the permutation group S4, which describes a downward rotation of the cube. That was a lot of big words. Feel free to rewind and play that back as many times as you need to. If we look at our cube from the front, on the face we started at, we see 4 vertices. 1, 2, 3, and 4. I'm intentionally ignoring the vertices that are in the background for the moment. Rotating the cube downward causes our 1, 2, 3, 4 cube to look like 4, 3, 1, 2. Specifically, after rotation, if we just look at the vertices on the front face, ignoring the ones in the background again, I see a 4 where the 1 used to be, a 3 where the 2 used to be, a 1 where the 3 used to be, and a 2 where the 4 used to be. We'll represent permutations in APL by their effect on this canonical 1, 2, 3, 4 cube. So an upward movement will be represented by the 4-element array consisting of 4, 3, 1, 2. Mario's state is represented by an element of S4, and elements in a group can always be composed together. So Mario's new state T is equal to his original state S, composed on the right with 4, 3, 1, 2. Now we can do the same thing for all of the other possible directions. Mario can walk off the top, left, right, or bottom of the cube. We just figured out that when Mario moves up, it corresponds to a downward rotation of the cube, which is written as 4, 3, 1, 2. If we walk off the bottom, that corresponds to an upward rotation of the cube, which results in a 3, 4, 2, 1 cube. Going to the left results in a rightward rotation, which results in a 4, 1, 2, 3 cube. Finally, going to the right is a leftward rotation, which results in a 2, 3, 4, 1 cube. Finally, it's also worth mentioning that a 90-degree rotation of the cube along the face that we can see results in a 2, 4, 1, 3 cube. Mario can't actually do this himself according to the problem description, but it'll come in handy in a moment. At long last, that's all of the theoretical background we're going to need. Let's see the code. We're going to figure out if Mario survived this galactic adventure by writing some APL. First, we'll define the variable r to contain the character array RULD. We'll refer to Mario's valid movement directions using uppercase letters. So the variable r contains all of the valid input instructions Mario can receive. Now we're going to define a function s, which takes one of Mario's movement directions, that is, one of the characters RULD, and returns the permutation array associated to it. So for instance, an input of u should return 4, 3, 1, 2 by our cube argument a moment ago. We'll write this as an explicit defun. First, we produce this matrix. We make a 16-element vector and reshape it to be a 4x4 matrix. Then we use dyadic quad to index into it. I've ordered this matrix so that the first row corresponds to right, the second to up, the third to left, and the fourth to down. That is, I put it in the same order as our r variable. Then we use dyadic iota to get the index of our argument character, omega, in the array r. Finally, we use that as the left-hand argument to dyadic quad to get a row from the matrix. Remember that omega is the right-hand argument, and in this case, the only argument to our defun. Now we're going to write a function called c, short for compose, which composes 2 elements of our permutation group S4 together. That is, it takes 2 4-element arrays describing the rotations of the cube and does them in order, performing the left one first and then the right one. It's actually pretty short, but let's go through it nonetheless. When we do so-called squad indexing with a nested array on the left-hand side, we select multiple elements from the right. So for each element in the left-hand array alpha, seek out its element at that position in the right-hand array omega. That is, permute the elements of omega using alpha as the permutation vector. That's exactly what a permutation vector is for. It permutes the input vector. Now we define P. P is a 24-element array whose elements are themselves arrays. P lists out all of the permutations of the cube. Let's see how we can do that efficiently. Left, up, left, up is a sequence of instructions that will visit each face of the cube exactly once. We apply S, which takes these directions and turns each of them into a permutation. At this point, we have an array of 5 permutation vectors. This is not a rank 2 matrix, it's an array of arrays. Now we scan with the backslash operator the compose dyad over this array. This produces an array of 5 elements consisting of 5 different faces of the cube. Finally, we prepend 1, 2, 3, 4, the initial state of the cube, onto the array by hand, making all 6 faces. We have the faces, but we need the rotations of the faces. So I need to take each element of this and rotate it 0 times, once, twice, and 3 times. This is a function that rotates the face we can see. Remember that 2, 4, 1, 3 is our rotate in place permutation from earlier, but we want to rotate it several times. We have a way to do something multiple times called the power operator, but it repeats its left argument, not its right. So switch the order of the arguments with the tilde diaresis, then repeat the operation a number of times equal to the left argument, alpha. Now we want to take our faces and rotate each face 0 times, once, twice, and thrice. Take the array 0, 1, 2, 3 of number of rotations on the left, and our faces array on the right, and apply this rotate number of times function using the outer or Cartesian product. This is a 4x6 matrix of permutation vectors. Make sure you understand that shape. This is a nested array whose outer shape is 4x6, and the inner shape is always a rank 1 vector. Specifically, this is a 4x6 matrix of permutation vectors where every element of S4 appears exactly once. I'm going to transpose this because it puts rotations of the same face next to each other and will make simplification easier later. Finally, ravel the result and get a 24-element vector of permutation vectors. Mario's position is going to be represented as a 3-tuple, S, Y, X, where Y and X are self-explanatory and S is an index into this P array. Now, remember ages ago when I showed the tessellation figure we had chosen? Here's that tessellation figure as a matrix, with 1s at the valid positions and 0s everywhere else. Just for a bit of fun, we can actually write this much shorter on one line using base 10 encoding. If we interpret this matrix, raveled as a base 2 number, it's the same as the base 10 number, 4,512,674,568. This doesn't actually add to readability, but we're way off the slippery slope of insanity at this point, so we're gonna go for it. So take that base 10 number, interpret it in base 2 by applying the inverse operation to the encode in base dyad, then prepend 3 leading zeros, reshape to a matrix, and assign to the variable v. This is Mario's starting position. He starts at y and x coordinates 4, 4. His state could really be any face of the cube we choose to start on, since the faces of the cube are all the same, so we just start on face 1. Now we're going to write a function called capital N. This function is going to be a big one. It takes a direction character on the left, one of either R, U, L, or D, and Mario's current position as a 3-tuple SYX on the right, and it returns a new 3-tuple SYX indicating Mario's new position. First, let's assume we're in the easy case. The easy case is where Mario doesn't walk off the edge of the cube. And in this case, we can simply shift his y and x coordinates without touching his state parameter. We make a matrix consisting of what to do in each of these cases. Right, up, left, down. If the instruction is right, we add 0, 1 to y, x. If the instruction is up, we add -1, 0 to y, x, and so on. Then we index into it using the position of alpha in our valid instruction string r. This is the same trick we used to get the permutation vector when we were writing the s function a moment ago. Once we have that, prepend to 0 since we're not changing Mario's state right now, and add it to Mario's current position. This doesn't change the state, but shifts y and x by the necessary amount. Finally, bind that array of 3 elements to s, y, and x. The left arrow will happily destructure an array if given multiple variables on the left-hand side. Now, in the unpleasant case where Mario does run off the edge, we can easily construct an array telling us what to do. This is a 2x2 matrix giving us instructions for all of the ways Mario can walk off the face of a cube. If he goes too far up, we add 5 to y and do a u instruction on the cube. If he goes left, we add 5 to x and apply an L instruction to the cube, and so on. Now to figure out which situation applies to us, we draw 2 lines across the tessellation figure. These 2 lines are given by the equation y plus x equals 7 and y minus x equals 0. We figure out which side of those lines Mario is on by using his y and x coordinates, then we index into our 2x2 matrix using the truth values of our inequalities. So if y plus x is less than or equal to 7 and y minus x is less than or equal to 0, we're in the top quadrant. Our index into the 2x2 matrix is 0, 0, so we get the U row. If y plus x is less than or equal to 7 and y minus x is greater than 0, we're on the left quadrant and our index is 0, 1. So we get the L row. If y plus x is greater than 7 and y minus x is less than or equal to 0, then we're in the right quadrant. And finally, if y plus x is greater than 7 and y minus x is greater than 0, then we're in the bottom quadrant. In any case, set capital Y and capital X equal to the change in y and x, and set t equal to the letter we need to apply. Now, all of this might be academic. After all, if Mario is still within the comfortable bounds of our tessellation figure, his state remains the same as it was before. Our tessellation figure is V, the two-dimensional array with a 1 at each position Mario is permitted to walk, and a 0 everywhere else. What we want right now is this. This is just V with a border of zeros around the outside. The zeros around the outside prevent us from running out of bounds when checking if Mario has, well, run out of bounds. We also replaced some of the invalid positions on our figure with 1s. This is just to protect us from going out of bounds. If Mario falls off the rhombocube octahedron, we need to be able to finish the program without error and print a false result, so we can't have our state check running off the edge of an array. And here's the magic sauce to produce that array. Let's break it down real quick. Take V, apply the take dyad with an argument of 8, 8. Our matrix is 6 by 6, so take is forced to pad with the fill element, which is 0 for our numerical matrix. At this point, our array has the correct number of zeros, just in the wrong places. We need to do some rotations to get them into the right places. Rotate the final axis to the left once, then rotate the first axis up once. Now, build the 1s in the center. We make a 4 by 4 array of 1s, take it up to 8 by 8, then rotate the 1s to the middle. Finally, join these two arrays together with dyadic OR. A lot happened there, but it was just a bunch of shuffling zeros around to get the shape we wanted. If Mario's position is at a 0 in the above array, we need to change states. This entire expression returns a 0 if Mario needs to change state, or a 1 otherwise. Now we use that value to index into two cases. In the case that Mario is fine, that is, in the 1 case, we simply return SYX, the original state and the calculated y and x positions. In the 0 case, the y and x coordinates are our transformed y, x, plus the shift amount we calculated earlier. As for the new state, we take the current state S, convert it to a permutation, compose it with the permutation associated with the rotation we just did, then convert the permutation back into a numerical state. Woo, that's a lot to take in, but that's the hardest piece. It's all downhill from here. Now we just have to put everything together. M is a monad which takes a sequence of directional instructions and returns a simple boolean indicating whether or not Mario survived. This is the main function for our program. Our initial grid is a 24 by 6 by 6 array, indicating where Mario has been. Since Mario hasn't been anywhere yet, we start off with an array of all zeros. Now, we take all of the prefixes to our input and we move Mario along those paths, giving us a vector of all of Mario's states. Tack on Mario's initial position to that array, since we clearly visit the starting position at least once. Now, for every state SYX that Mario visits, we go to that position in our T array and add 1 to it. Next, it's time to simplify our cube, because we've been lying to ourselves a bit. We keep saying that Mario has 24 possible states he can be in, and that's a useful abstraction for keeping track of Mario's orientation. But in reality, there are only 6 faces to the cube, so we need to collapse the rotations. If Mario visits the same position twice, even if he was facing a different way, we should get a failure result. Take T, the 24 by 6 by 6 array of all states Mario visited, and close it along the state axis. This gives us a 24-element vector of 6 by 6 matrices. We want to rotate all of these so that they represent reality. Currently, the first 4 of these matrices represent the same face of a cube, but each one rotated by a different amount. Let's fix that. Rotate the first element 90 degrees once, rotate the second one 90 degrees twice, the third one thrice, then 4 times, then once, twice, thrice, 4 times, and so on. Now mix the array, which is sort of the inverse of enclose. This gives us our 24 by 6 by 6 array again. Then reshape it to be a 6 by 4 by 6 by 6 tensor. Yes, you heard that right. This is a rank 4 tensor whose axes are, in order, face, rotation, y, and x. Now, sum along the second axis, or the rotation axis. This gives us a 6 by 6 by 6 array of face, y, x, which exactly represents where Mario went. V tells us where Mario is allowed to visit on each face. Reshape it to be 6 by 6 by 6, repeating the tessellation figure for each face, then subtract Mario's actual path from it. If we ever end up with a negative number anywhere in this 6 by 6 by 6 grid, then Mario either went somewhere twice, or he went off an edge where there wasn't a platform. So finally, check if any position is less than 0, and return the result. And this solves Mario's rhombocube octahedron problem in APL. We can pass it any sequence of instructions, and the capital M monad will give us a 1 if Mario survives, or a 0 otherwise. Tune in next time on our regular schedule when we solve Project Euler problem number 22 in Elixir.